So for those of you who may think they're already lost because they don't know what the solar wind or the magnetosphere is, do not worry. We will go through that in quite detail, and hopefully by the end of this you'll be able to understand what that is and get a better idea of what's going on in this region of space. So before we get into the science, I'm going to talk a little bit about how I got to this place and what different people are doing in magnetospheric physics. So I started, let's see if we have a cursor here, yep. So I grew up in a small town called Carlisle in the northeast of the United States. It was a very rural town. There's not much going on there, but they are known for their small red berries called cranberries. They're kind of a bitter or tart berry. After that, I moved on to Colgate University in the top right panel here. At Colgate University, I studied physics. I also studied astronomy, and my focus there was looking at neutral hydrogen in galaxies. We could look at how galaxies form, the rotation rates, and things like that. But I think probably the most important part coming out of that was I had a strong background in physics. And before getting into all the nitty-gritty or the details of how different fields work, getting a strong background in physics is very important. On the bottom left here, we're moving down to the bottom left now. After Colgate University, I went on to Boston University. And at Boston University, it was a much larger school and learned a lot more about space physics and about how things operate inside our own solar system and the dynamic interaction between the sun and the planets and the magnetic fields around planets. This was an area I had no idea even existed until I got to graduate school. After graduate school, or after Boston University, I moved on to where I am right now. That's the NASA Goddard Space Flight Center, and this is even a larger facility. At the NASA Goddard Space Flight Center, there are people from lots of different backgrounds, engineers, aerospace people, scientists, and all these people come together, and it's a really great atmosphere of creativity and merging of these different expertise. So a little bit before I get too much into the science, the format we're going to be going through today, or I'm adopting here, is we're going to look at kind of a historical perspective. So we're going to see how ideas have developed over time and see how they build off each other to develop the understanding we have today. So arguably the start of space physics, or the start of magnetospheric physics, and the magnetosphere is the region around the Earth dominated by the Earth's magnetic field. So the start of this field, or this idea, came from William Gilbert. William Gilbert, like many people of his time that are famous for physics, was actually quite talented at many things. He was a physician as well as a physicist, and as a physician he was the private doctor of Queen Elizabeth I, so he was very successful at that as well. But to us, probably his greatest contribution, at least to me, is that he came up with the concept that the Earth is a magnet. And so this might seem pretty basic to people here today, but at the time this was not known. And maybe they should have known it because people used compasses for many years before William Gilbert, but they weren't exactly sure how their compass worked. They always knew that it pointed northward, but they weren't sure what was causing this. Some people thought that the North Star itself was a very strong magnet, and so the compass needle would point towards the North Star. Other people thought that there was an island near the northern pole of the Earth, and that pole or that island contained strong magnetic fields. Fortunately, these have passed away, and the primary idea now is that the Earth is a magnet, which is an important contribution. And later we find out that other planets as well are also magnetic. And on the right here is a picture of the cover of the book he wrote, and he coined or called the Earth a terrella, and that was his word he termed for it. So we're going to skip a number of years now, and there's a large amount of contributions and things that were learned from the surface of the Earth, but we also had great development once we were able to leave the surface of the Earth, once we were able to actually put sensors up into space to measure what's going on up there. And the first spacecraft to do that was Sputnik in 1957. This was put up by the Soviet Union. And if you look on the left here, it looks like a basketball. It's kind of an orange color, and that's actually about the size of it as well. It was just a little bit larger than a basketball. You see there are 4 antennas coming off it. But if you look at this and think about satellites you see now, or at least see pictures of now, and this, there's one large difference, and that's there are no solar panels on this. And that was part of the early design by the Soviet Union, they were very eager to put things into space, and they said, well, we could develop solar panel technology, or we could just launch right away and show our capabilities. And so they opted for the latter, which was good. And to give you a little bit of an idea, because they're not using solar panels, they're using batteries. And because of this, batteries only last so long, and it was only able to last 22 days until the batteries themselves died. The spacecraft remained in orbit for about 3 months before it burnt up in the atmosphere. And the contribution from the batteries was most of the mass on this spacecraft. The mass of the entire thing was about 184 pounds, but for you guys in Bulgaria, that was about 83 kilograms. And of those 83 kilograms of the full mass, 51 came from the power supply. So by using smaller batteries and solar panels, we're able to do a lot better these days. So just 1 year later, or a little bit less than a year later, the Americans put up the Explorer 1 spacecraft. And on the bottom right here, there's a somewhat famous picture of William Pickering, James Van Allen in the middle, and on the far right, Wernher von Braun. And these were three very influential and important people in the development of rockets and early technologies. And Explorer 1 was particularly useful, or particularly famous, because of the discovery of the Van Allen belts, or the radiation belts. We're going to talk a little bit about that coming up, but I wanted to point that out now. And this was not only a demonstration of rocket capability and the capability to put something into orbit, but there was also scientific instruments on this. And through the scientific instruments, they were able to measure some of the early properties of the near-Earth space environment. So these two launches spurred a space race between the USSR, or the Soviet Union, and the United States. This was both good and bad. Bad in that there were kind of hard feelings somewhat between the countries, but it was great in terms of the development of space technology, of education. There was more money put into education, into our core sciences during this period than any other period that we've seen. It was really quite remarkable. And in addition to just the space technology that was being developed, there were tremendous amounts of spin-off technologies as well. So I'll go through a few pictures here I added for firsts that were developed during this time period. There was, even before the Explorer went up, Sputnik 2 went up, and that was the first time an animal was ever in space, and that was a dog named Laika. We have a picture of her here. On the right, there's a first human in space that came from a cosmonaut named Yuri Gagarin. This was early in the time. They didn't quite have the technology to land a spacecraft with a human, but they had an ejection seat, or an ejection, and he would parachute down, and that's how the spacecraft and launch went. He was able to stay in space for a little over 100 minutes, so 108 minutes, and so that was roughly one orbit. For those of you guys at home, I know that you guys are working on a CubeSat. If you can think about maybe some of the programming you're doing, in this first manned spaceflight, although the entire thing ended up being an autopilot, he had the capability to go and control things himself. But because at the time their interfaces were very primitive, the only capability he had to go into autopilot was to go and enter things via command line. So if you guys are thinking about some of the coding that you're doing, if you have just a comma in a wrong place, or if you flip a decimal point, you can see very different effects. Well, that's one of the things he had to deal with if he was going to try to control himself. So in the end, he did not control himself. Alright, so now we're moving around this from first human in space to first human on the moon. And the United States, through the Apollo program, was able to put people on the moon. It's actually a picture here of Buzz Aldrin, but on the bottom it states correctly that the first human on the moon was Neil Armstrong. And the bottom right was the launch of one of the Apollo programs as well. Okay, so now we have a video here. So I'm going to start this. So this is a video of some of the footage from the moon. And so you see people driving around and some of the experience they had. And so you can see on this little moon rover here, they've got a bunch of cameras, they've got a person driving, but they also have a number of scientific instruments. And so on the previous slide we showed that there are a number of firsts. First man on the moon, first human in space, first animal. But in addition to just first, a list of firsts that we can kind of put check marks and show for for prestige and things like that, we're also able to take a large number of scientific measurements. And this is very important for our understanding of how the space environment around us works, how the physics works. They were able to measure magnetic and electric fields, as well as able to make particle measurements. And these particle measurements were very useful from these scientific instruments they brought up into space. But another contribution they were able to give, which was somewhat frightening at the time, was the contribution of the human body. And one of the things they were able to notice very early in the Apollo program was that when some of the astronauts would go into their space quarters and close their eyes to go to sleep, they would close their eyes, and instead of just seeing black, as they would expect to see and they see on Earth, they saw these flashes of light, just bang, bang. And they realized eventually that these flashes of light were energetic particles traveling through their eyelid and hitting their retina. And so this contribution of space radiation, of energetic particles hitting the body, was a concern they weren't really aware of, and not everyone was aware of before the launch of these spacecraft. And so we're able to understand some of the dangers going up there as well. If they were going up there during a very hazardous time, there could be lots and lots of these energetic particles, and it could cause a lot of illnesses in the astronauts. This was also something that you guys will be concerned about in development of your CubeSat. The radiation environment can be very hazardous for spacecraft as well as people up there. Okay, so this brings us to the idea of space weather. And space weather is the idea, or partially the idea, that things are not just constant up in space. Once you leave the atmosphere of the Earth, it's not just empty space between here and the next star, that there's actually a lot going on out there. And so we have a cartoon, or an artist's rendition here. On the left, there's the sun, and on the right, we have the Earth in the middle. These kind of blue wispy lines coming off it are the Earth's magnetic field. And you can see the Earth's magnetic field is being impacted by the sun on the left. And the impact of the sun is what generates space weather. You've got sometimes the sun is generating lots of explosions and loud things, or maybe not loud, but intense things coming off its surface. As they come radially outward and contact the Earth, you can see dynamic effects. So one example I've got a picture of, or a video of here, and so this comes from the SOHO spacecraft, and this is going to be a picture of the sun, or a video of the sun. The sun itself is actually right behind the black disk in the middle. Let's see if we get our cursor up again. The sun is actually behind this disk. And you might be thinking to yourself, what kind of a picture, what kind of a camera is this if they're covering up the best part? They're covering up the sun. And the explanation to that is fairly simple, and that's this camera was actually designed to measure the atmosphere of the sun, or the outer parts of the sun. And the disk of the sun itself is just too bright, and they can't see the atmosphere if they have the disk in the image. So they've got this, what's called a coronagraph, and this little arm up here, and then this disk covering it. So once I hit play, you're going to start seeing things coming off the surface of the sun. And typically you can see on a calm day, or a normal day, you can see stars in this picture. All these little white dots are likely stars. But during a disturbed period, sometimes this vision gets distorted. So I'm going to hit play now, if I can figure out how. Okay, here we are. And so you can see coming off the northern pole, there's some filaments, and boom, there's an explosion right there. And now you've got all these little white things, all these little white marks hitting the camera. Okay, so what these white marks are actually charged particles hitting the camera. And this camera is built based on a technology, a CCD, a charge-coupled device. And if you think about maybe some of your phones have cameras on it, or if you think about a digital camera, this is built roughly the same way. And if you have a charged particle that slams into the surface of that camera, you're going to have a little white spot. And so all of these charged particles can cause dangers to space, to astronauts, to people who are out of the protection of the Earth's magnetic field. Another thing they can cause harm to is spacecraft. So we have a spacecraft that just popped up here. This can cause damage in a number of ways. One, it can do problems for navigation. Some of these spacecraft navigate via star trackers, which means they look for different patterns in the stars with little cameras that point out in the sky. But if you see this camera on the left, or this picture on the left, we have all these energetic particles that are slamming into it. And if these particles are slamming into our star tracker, we're not going to know where the stars are accurately, because we have all these other things that look just like stars. Another thing that this can impact, which something you should certainly consider in the development of your CubeSat, is these energetic particles can impact the memory or the communications of your spacecraft itself. If you think about how code is or information is stored digitally, you have a number of ones and zeros. And if one of these energetic particles slams into one of your chips, it can flip a 1 to a 0, which can have a large effect. And another thing to point out here is that something from the sun is coming off called the solar wind. And that's flowing radially off the solar wind in all directions, pretty much all the time. And the intensity or the strength of the solar wind will change throughout the time period. Okay, so now we're going to look a little bit more, moving closer to the Earth, about the Earth's magnetic field. On the left is the simplest approximation. We noted before that the Earth's magnetic field, or the Earth has a magnetic field, and it's a very rough approximation. You can say it's a dipole magnetic field. So if you think about a dipole magnet that maybe you have sitting around your home, and put that, a very, very large one, on the inside of the Earth, that gives you roughly what you see. You have magnetic field lines that come from, if I can find my cursor, from one pole to the other pole. And it's slightly offset. It doesn't go completely north-south. Now if we take that and make a little bit more complex picture and move to the right of this slide we have here, we see what we have is the yellow now field lines, or the yellow traces are the magnetic field lines. And this is the interaction of the solar wind with the Earth and the Earth's magnetic field. So from left to right, we have flowing solar wind coming with these dashed lines and arrows. And the solar wind is supersonic, so it needs to form a shock before it reaches the obstacle of the Earth and the Earth's magnetic field. Once it travels through this green line here, which is the shock, or the bow shock, it starts to get it's slowed and starts to get deflected around the Earth and the Earth's magnetic field. This pink line here is the magnetopause, and that divides the region dominated by the flowing solar wind with the region dominated by the Earth's magnetic field. Now both of these pictures here are staying still, they're not movies. And that means that we're going to have to get even more complicated. We're going to have to move from a static picture or a stationary image of this or mindset into a dynamic picture. And so that's what we're going to do here. The previous pictures were also cartoons or artist renditions of the magnetosphere. This is more physics-based. So this is a model generated by magnetohydrodynamic theory, and the color is showing density. Well, I'm going to hit play eventually. First I'll describe what's going on. The Earth is right here. The gray is showing the Earth's magnetosphere, or the magnetic field. You see this outer boundary, this is the bow shock. And this circle here shows the aurora, or the northern aurora. And once I hit play, you're going to see the solar wind comes at different magnitudes. Sometimes it's strong, sometimes it's soft, comes in slightly different directions. And then the Earth's magnetosphere reacts to that, kind of like a windsock in a variable wind. So you can see here the tail part, or the night side part of the magnetic field. Sometimes it stretches very far, sometimes it contracts, sometimes the solar wind blows hard and the whole magnetosphere, or the Earth's magnetic field, contracts and makes very small. Sometimes it expands. And because of these dynamic features, because things are changing, you're going to have things changing inside the magnetosphere as well. And so there are a number of effects that we can see from the Earth, and there are a number of effects we see in space. And these are some of the interesting things that people are studying right now in the magnetosphere. So one thing we can see is called magnetic disturbances, and this is probably one of the oldest things that people have measured, looking at the connection between the sun and structures coming off the sun and the Earth's magnetic field. So on the left here we have a schematic diagram where each one of these black lines or black horizontal lines represents a ground-based magnetometer. And one of these ground-based magnetometers are shown by each black dot on the surface of the Earth here. This happens to be generated by an American organization in the United States, so we have the United States showing here. But of course these magnetometers are distributed all around the world. And so a magnetometer is just a simple device that measures the amplitude and direction of a magnetic field. So you can see a number of different impacts here, effects on the lower traces going across. There's very little impact. There's very little variability in the magnetic field. But as we get higher and higher up, these are higher and higher latitude, closer to the pole, and you can see there's lots of shaking around, there's lots of variability. And this came from a time when this large structure came off the sun and impacted the Earth's magnetic field. So you can see it compress, and some of these compressions and some of these waves were propagated all the way down to the Earth's surface. And part of the reason this was measured from so long ago is we didn't have to go into space. You could set up magnetometers on Earth, as shown in a picture on the bottom right here. People could measure these from a number of places on Earth. And in efforts to quantify how large an impact is, there was an index generated, or a number of indexes, but one of them I mentioned here will be called the KP index. And we'll just remember that name, KP index, for a little bit later, as it will come up again. During times of very large variability, large structures impacting the Earth, you're going to have a large KP index. On a very calm and normal day, not much is going on, we have a low KP index. Another impact on the Earth, or another thing you can see on the Earth from space weather, is aurora. And aurora, we might think now of beautiful things in the sky, but that was not always the understanding. We'll go through a little bit of a timeline here, a few different pictures that people once thought of. The first mention of it came from China, from an individual in China at 2600 BC, a very long time ago. And between that and now, there's been a whole slew of different predictions of what is causing these things. I have one that I found entertaining here from 1570, this cartoon here. And this was by a physicist that thought the aurora was above the stars. And so you have your village down here, and then there's stars, and then above the stars there was this aurora. And this cartoon here, he has what looks to me like birthday candles flickering on and off and causing the aurora. Another misfire came a little bit later by Galileo, who, although produced many wonderful ideas to the field of physics, was a little bit off on this one. He actually coined the term aurora, or aurora borealis, which is still used today, but his explanation of the cause of aurora was a little bit off. He said aurora was caused by reflection of morning light. He thought it should only happen near sunrise, and that's why he actually called it Aurora, which is the Roman goddess of morning. But now we know that the aurora can happen any time at night and is not just reflected sunlight. A great development came in 1903 by a Norwegian scientist named Birkeland, and he concluded that the aurora was caused by currents flowing through our upper atmosphere. And this is pretty close to what we think it is today. Birkeland would go up there with his science team up to very high latitudes and cold nights, and he would sit there with these devices, magnetometers, on the surface of our Earth, measure the magnitude and the direction of magnetic field, and then look up and look at the aurora. And they saw lots of connections there. They said when we see very strong aurora, we see large disruptions in the magnetic field at the Earth. And from this they concluded that we've got currents flowing down and precipitating into our atmosphere. And now our current day picture is shown in this cartoon here, and that's really not far from what Birkeland had, and I guess that's why his ideas were so influential. They put him on a note in Norway, as you see in the picture on the bottom left here. And so the general understanding we have now is that we have charged particles, electrons and ions, that flow along magnetic field lines and slam into the dense atmosphere of the Earth. When they flow and slam into the atmosphere, these charged particles collide with neutrals. When these neutrals are energized or excited to higher charge states, eventually they drop down to lower charge states and they give off light. And this light is from the aurora, from the molecules. And so we have two pictures here. One is from a spacecraft looking down. This is from the Polar spacecraft, and this is a UV imager. And you can see there is somewhat of an auroral oval that forms. On the right we have just a picture from the Earth. And you might think, oh, these colors, these beautiful auroral colors, look similar to what I see in neon signs. And the reason for that is this is actually pretty much the same process going on in neon signs. You've got currents flowing through gases, and that causes this emission of light. And depending upon the gas you have in your neon sign or in the atmosphere, you're going to have different color aurora. So in the picture on the right here, we have primarily green aurora, and it's often called green line aurora, which typically comes from oxygen. Sometimes you can see red colors as well, and that comes from helium, as well as a number of other colors from different gases. So here's a plot from NOAA, which is an organization in the United States that does space weather predictions. And they have a plot here predicting when and where you should see aurora under different levels of geomagnetic activity. And you see a map of part of the Earth here, and you see these colored lines coming, and each one corresponds to one KP index level. And if you remember before, we noted that KP, a higher KP would mean a more disturbed time, and that means the aurora can be seen closer towards the equator. And this map here unfortunately shows that it's very unlikely, probably won't happen even, at least during current storms, that you will be able to see aurora in Bulgaria. Sorry about that. Another impact of these space weather impacts or effects is the trapped particle population in the Earth's magnetic field. So these are often called the radiation belts or the Van Allen belts, and we'll start on the top left here to give you a little bit of a schematic diagram of what's going on. So a charged particle, an electron or a proton, will gyrate in a circular motion around a magnetic field. And this is caused by something called the Lorentz force. As this particle gyrates around a magnetic field, it will also follow that magnetic field. And remember, the Earth has somewhat of a dipole field, so these particles will just bounce back and forth, back and forth. And it can also drift. And because of this somewhat steady bouncing periodic motion, you have this radiation belt that forms. And the bottom left shows a picture of that. You can see a torus is formed here. You get very close to the Earth, near the equator, very little radiation, but if you get further and further out, you have more and more. And these are called the Earth's radiation belts. And typically you have fairly high energies from 0.1 to 10 MeV, mega electron volts. And because of this trapped physics, you can have lifetimes. These particles can last from hours to even years just drifting around the Earth before it gets scattered and lost. Some of the causes of this are wave-particle interactions, radial diffusion, as well as man-made causes. And sometimes, or at least in the 1970s, there was an experiment that a number of countries participated in that detonated atomic weapons in the upper atmosphere. And these caused generation of tremendous amounts of high-energy particles, and they were seen in the Earth's radiation belts trapped consistently for even months. And I will note here that this is also the target of NASA's current Van Allen probes that were launched just about a year ago. And there are two spacecraft in very similar orbits orbiting around looking at this very high energy population. And this is something you really need to be concerned about in terms of CubeSat generation or CubeSat production. That's thought to be one of the main mechanisms that kills CubeSats. So you need to think about what your orbit is, what the type of radiation that you will experience is, and think about that in terms of how long you want your CubeSat to last or how long you expect it to last. Another term that I'd like to introduce here is something called the L-shell. And the L-shell is essentially radial distance from the Earth at the equator. So we have it drawn here. So if you get larger L-shell, you're further from the Earth. Okay, now we mentioned that the radiation belts and particle dynamics will change with the solar wind. This is a figure here showing that to be the case. So the x-axis of the bottom plot, or both plots, is time in years from 1993 to 2004 over almost a full solar cycle. The y-axis of the bottom plot is showing L-shell, or L value. So as we just showed or explained, close to the Earth, L-shell of 1 or L-shell low. Further from the Earth, you have higher L-shell. On this top panel here, we're showing two things. One is sunspot numbers, which is an indicator of solar cycle or phase of the solar cycle. And the second piece it's showing in red is a solar wind velocity, so how strong it's blowing at the Earth. And you can see some correlations here, and you can see a number of different impacts. First, you might see, well, this isn't just a solid red bar going across here. Sometimes the solar wind is very strong, or sorry, sometimes the radiation belts are very intense. You have very high electron flux, and that's what the color is showing. But sometimes you have very low electron flux as well, and sometimes there's not much going on. The center of this distribution changes in L-shell. Sometimes it's closer to the Earth, sometimes it's further away. And if you look closely, you might see some connection with the solar wind velocity. You can see here there's a very large jump or a large intensity of solar wind velocity. That corresponds to this time period here when you have very large fluxes in energetic electrons. And that's an interplay between the solar wind exciting the Earth's magnetosphere and causing these energetic, very high energy particles in the Earth's radiation belts. So we will now move on to kind of a larger picture called space weather. And we have a number of pictures here. We've got pictures of impacts of space weather on things we observe at Earth. And see, okay, we'll move around to a few of these. One is that energetic particles can slam into the actual spacecraft and cause damage to, it can impact cameras, it can cause damage to detectors, as well as just the memory on the spacecraft. Another piece that can impact is GPS signals. The atmosphere, the upper atmosphere itself of the Earth is called the ionosphere, and that becomes very dense, lots and lots of electrons density during strong storms or large disturbed periods. And when that happens, it's difficult to send signals from our GPS satellites down to the Earth, and we often miss packets, and our signals get distorted. Another thing that is important and that people on Earth take into account is the impact of the radiation coming down on humans. A number of flights that would typically fly over, so airline flights we're talking about here, a number of airlines that would fly typically over the poles will get diverted to lower latitudes during large geomagnetic storms. And the reason for that is because of the radiation and the impact on the crew as well as the navigation. In time periods when you're flying over the poles, you can have access of charged particles, just like we saw the aurora going into the pole. These charged particles can go through the spacecraft and hit the people on the flight as well as the avionics. There are a number of other impacts that are shown here. I'm not going to go through all of them. We're running a little bit late, but I think you guys are going to have access to this PowerPoint presentation so you can take a little bit closer look here a little bit later on your own time. And so I've got a movie here showing that the public is becoming more aware of these space weather effects. During the time of the space race and the early days of space physics, we didn't really know all the impact of space weather, but now scientists are getting to know it as well as the public community. So
but there's another huge star making headlines this week, and
this
one
hopefully playing, hopefully not too loud though. So this is Jon Stewart talking about
which in less than 48 hours has emitted
some of the
two
impacts.
massive bursts of electrified gas at the Earth. The first of these disruptive solar flares took place Wednesday, buffeting our planet's magnetosphere. Why, God? Why must you let bad things buffet good magnetospheres? Oh, magnetosphere! The flare caused a series of geomagnetic storms across our atmosphere, leading to disruptions in radio signals, airplane communications, and satellite operations. Oh, and there was also this.
All right. We will stop it at that point. But that's just an example showing that the public is becoming more aware, and this is more important for people other than just scientists. There are programmatic needs for this, people doing different things in aerospace, and they need to know what's going on in space physics. This is a comedian talking about it here, but it is important. So now we're going to look forward. I just have another slide or two taking a picture of looking forward and what other opportunities we have and opportunities coming up. We have two things here. One is that there are very large opportunities coming up. The MMS spacecraft is being launched or is scheduled to launch in 2014. You can see a picture of how large they are on the right here. These are people, and these are 2 of the 4 spacecraft that will be launched. And so these are very large spacecraft, a fairly expensive mission, but it will be producing great science output. There are 2 other missions that were just announced. One is ICON, and the other one is called GOLD. These are other NASA missions to look at the lower magnetosphere, where the magnetosphere and ionosphere couple with the atmosphere, the neutral atmosphere. So that's one direction you can go in. You can make much larger spacecraft. But another direction you can go in, which you guys are also getting involved in, is doing very small. And this is a really great way to do it as well. You can do more prototyping. You have more ability to take on risks because it's less expensive. And I have just one example here. There's one called Firebird, which is being put together and operated by Montana State University, as well as University of New Hampshire in the United States. And that should launch coming up this fall, I believe. And on the right here, it's showing pictures of it. This is actually a 1.5U CubeSat, and this is the detector right here. It's going to be measuring energetic electrons. Okay, and in addition to DAT-1 CubeSat, there's a NASA program going on right now called the CubeSat Launch Initiative, and that recently came up with selections of a whole slew of CubeSats that it's willing to and is planning on launching. This is just a map of where all the selections from 2013 were, and this is showing, I believe, 25 new CubeSats that will be launched through this initiative. There's no launch date yet, but these are all different institutes and different programs around the United States that will be launching CubeSats. So in terms of collaborating, this would be great for you guys to maybe think about this, talk to some of these groups, talk to them about what's worked, what hasn't worked, and hopefully learn a little bit about what to do next time. All right, so that concludes the talk today.